Our map of the universe is being redrawn before our eyes. Every few weeks, a new observation shatters an old assumption, revealing a cosmos more bizarre and dynamic than we ever dreamed. This is a journey through 25 of the most startling new space phenomena, discoveries that are actively rewriting the textbooks. By the end, you will see the night sky not as a static picture, but as a living, breathing arena of endless mystery. We now find ghostly rings in the void larger than galaxies, and black holes flung from their homes like cosmic cannonballs. What do you believe is waiting for us in the dark? Among these new cosmic signatures, few are as visually puzzling as the odd radio circles. Discovered only a few years ago by radio telescopes, these are colossal, faint rings that glow only in the radio part of the light spectrum. They are not visible in optical, infrared, or X-ray light at all. Each one is an island in the sky, so vast it could easily contain an entire galaxy within its circumference. And yet, for all their size, they are ghostly, leaving no trace in any other form of light we can detect. They simply hang in the void, silent and enigmatic. Their origin is a complete puzzle. They do not match the profile of any known object. They are not the leftover shells of supernova explosions, which are usually more chaotic and filled with intricate structure. They are not the jets from active black holes, which typically appear as paired beams, not perfect circles. So what carved these perfect rings into the fabric of space itself? The leading ideas are as dramatic as the objects themselves. One theory suggests they are the titanic shockwaves produced by galactic winds, streams of particles blowing out from a galaxy's core at incredible speeds, slamming into the thin gas between galaxies and creating a spherical ripple. Another, even more explosive idea is that they are the aftermath of a cosmic merger event so violent it sent a sphere of energy blasting outward in all directions. What is most profound is that, regardless of which theory proves correct, the odd radio circles represent something fundamental, an entirely new class of astronomical object that we simply did not have a name for until now. They remind us that our catalogue of the cosmos is still missing entire chapters. While ghostly rings hover in the void, other cosmic titans are in violent motion. Astronomers have captured what appears to be a supermassive black hole, an object with the mass of 20 million suns fleeing its home galaxy. The Hubble Space Telescope revealed a breathtaking sight, a brilliant streak of light over 200,000 light-years long, like a cosmic brushstroke painted across the darkness. At the tip of this streak is the black hole itself, a point of intense energy, and trailing behind it is not destruction but creation, a luminous corridor of newborn stars. This is not a trail of debris, it is a stellar nursery ignited in the black hole's chaotic wake. The prevailing theory is as cinematic as the image. Scientists believe this began when two galaxies merged, each with its own central, supermassive black hole. As these monstrous objects circled each other, they churned the fabric of space-time, emitting powerful ripples called gravitational waves. If the waves were emitted more strongly in one direction, the resulting recoil could have kicked the newly merged black hole clear out of the galactic core, like a rocket firing in one direction and shooting off in the other. As it plows through the galaxy's surrounding gas at tremendous speed, the gas compresses and cools along its path, triggering the birth of those stars. This single observation forces us to rethink fundamental ideas. It suggests that black holes are not always anchored at the heart of galaxies. They can be sent wandering through intergalactic space. It shows that the most violent events in the universe can have creative consequences, forging new suns from chaos, and it provides a potential explanation for a long-standing mystery, why we sometimes find massive black holes isolated in the vast, empty tracts between galaxies. They may not have formed there alone, they might be runaways cast out from their homes by the physics of a colossal merger. But for every runaway giant, there must be countless smaller exiles. The first definitive proof of a completely isolated, wandering black hole came not from a brilliant streak of light, but from a subtle distortion of starlight. After decades of searching, astronomers using a technique called gravitational microlensing finally spotted a lone black hole drifting silently through the interstellar darkness of our own galaxy. This method relies on a beautiful trick of gravity. When a massive object like a black hole passes almost directly between Earth and a distant star, its immense gravity acts like a lens, bending and magnifying the star's light. For a brief period, the background star appears to brighten in a very specific telltale way. By meticulously tracking this brightening event with both the Hubble Space Telescope and a network of ground-based observatories, scientists could measure two crucial things: the mass of the invisible lens and its motion across the sky. The data revealed an object roughly 7 times the mass of our Sun, drifting at about 160,000 kilometers per hour and emitting no light of its own. Only a black hole fit the profile perfectly. This solitary wanderer, located about 5,000 light-years away, is a stellar mass black hole, the ghost of a massive star that died in a supernova long ago. The explosion was likely asymmetrical, giving the remnant a kick that sent it sailing away from its birthplace, unattached to any star system. The profound implication is statistical. If we have found one, there must be many, perhaps even tens of millions of these dark nomads adrift in the Milky Way alone. They are the invisible infrastructure of our galaxy, unseen masses weaving through the star fields, their presence only betrayed by the occasional, fleeting warp of a distant star's light. This detection transforms our understanding of the galactic population, suggesting that for every black hole we see in a binary system, feasting on a companion star, there could be many more leading quiet, solitary lives in the vast dark between the stars. While solitary black holes warp starlight from the shadows, another form of cosmic lensing can transform a single, ordinary star into a beacon visible across the universe. This is the story of the star nicknamed Mothra, a celestial giant whose light was magnified not by chance but by a perfect and fragile alignment of cosmic scales. To understand this, we must think of gravity not just as a force but as a landscape. A massive object like a galaxy cluster warps the space around it, creating a kind of lens. When a distant star, a galaxy, and our telescopes line up just right behind this lens, the star's light is bent and focused, often into multiple images or a dramatic brightening. But Mothra's case is extraordinarily special. Here, the primary lens is a vast galaxy cluster. Yet within that cluster, a single star happened to drift into exactly the right position to act as a second, tiny lens within the giant one. This created a phenomenon called a caustic, a point of theoretically infinite magnification within the gravitational lens. It is the difference between using a magnifying glass and then finding a tiny, perfect flaw in that glass that focuses sunlight into a scorching, pinpoint beam. For a brief period, that beam was pointed directly at a single, massive star in a galaxy so far away its light has been traveling for over 12 billion years. That star, Mothra, was magnified thousands of times, allowing astronomers to study an individual star at a distance normally reserved for studying entire galaxies. This is not just seeing a pinprick of light, it is analyzing its composition, its temperature, its size, from an era when the universe was a fraction of its current age. Mothra is likely a supergiant, hundreds of times larger and millions of times brighter than our Sun, a cosmic monster made visible by a 1 in a million celestial alignment. Its brief, magnified brilliance is a gift, a direct window into the lives of the first generations of stars that lit up the cosmic dawn, showing us the building blocks of early galaxies, one brilliant giant at a time. The universe holds places of profound cold that defy our earthly experience, and none is more extreme than the Boomerang Nebula. For decades, this faint, distant cloud has held the title of the coldest natural place we know of, with temperatures plunging to just 1 degree above absolute zero. But recent observations from the powerful ALMA telescope array have done more than just confirm its chill. They have completely reshaped our vision of this cosmic icebox. The iconic boomerang shape visible in earlier Hubble images was revealed to be an illusion of perspective. ALMA exquisite resolution, seeing in millimeter wavelengths that pierce through dust, showed the nebula's true form, a sprawling, elongated hourglass stretching over 3 trillion kilometers. This ghostly structure is not a static sculpture of ice, it is a dynamic and violent wind. The data captured the nebula's gas screaming outward from a central, dying star at a breathtaking speed of over 150 kilometers per second. This is the key to understanding the deep cold. In a process similar to how a refrigerator works, when a gas expands rapidly, it cools. Here, the star at the nebula's heart is in its final throes, shedding its outer layers in 2 opposing supersonic jets. This bipolar outflow is expanding so fast and so efficiently that it drags the surrounding gas with it, creating that vast, frigid hourglass and cooling it to a temperature lower than even the faint background glow of the Big Bang. This transforms the boomerang from a simple curiosity into a vital lesson in stellar physics. It shows us the dramatic, sculpting power of a star's last breaths, a preview of what will happen to our own sun billions of years from now. In its exquisite, frozen detail, we see the precise mechanics of how an ordinary star begins its transformation into a planetary nebula, trading its heat for a legacy of intricate beauty carved into the depths of space. The deep freeze of a dying star stands in stark contrast to the searing, toxic clouds of our closest planetary neighbor, Venus. Here, a single molecule has ignited one of the most heated scientific debates of our time, a controversy centered on a gas called phosphine. On Earth, this simple compound, made of 1 phosphorus and 3 hydrogen atoms, is almost exclusively linked to life. It is produced by microbes in oxygen-free environments like swamps and, tellingly, in the intestines of animals. It is not a gas we expect to find floating in abundance on a hellish, scorching world. Yet in 2020, a team of astronomers announced they had detected its spectral signature in the temperate, upper cloud decks of Venus, a region where pressures and temperatures are surprisingly Earth-like, though bathed in sulfuric acid. The claim was explosive, suggesting the possibility, however remote, of aerial microbial life floating high above the Venusian surface. The scientific community reacted not with celebration but with intense scrutiny. This is how science corrects itself. Multiple teams rushed to reanalyze the same radio telescope data. Some could not find the signal at all, suggesting it might have been a statistical fluke or an artifact of the complex data processing. Others proposed the signal could be explained by sulfur dioxide, a common Venusian gas, confusing the readings. The original team stood by their analysis, and newer observations added more puzzling, tentative detections, keeping the mystery very much alive. Why is this debate so profound? Because all known geological and chemical processes on Venus, from volcanic activity to lightning strikes to the interaction of sunlight with its atmosphere, struggle to produce phosphine in the quantities suggested. The planet should be destroying the molecule faster than it can create it. So if phosphine is truly there, something unexpected is happening. The possibilities stretch our imagination. It could point to exotic, unknown atmospheric chemistry we simply do not yet understand, a new branch of planetary science waiting to be written. Or it keeps ajar a door that many thought was sealed shut, the door to the idea that life, in some incredibly hardy form, might find a way in the most unexpected places. This is not a discovery, but a persistent, tantalizing question mark hanging in the alien skies next door, a reminder that sometimes the most significant finding is not an answer, but a mystery that refuses to go away. The search for life often leads us to the most unexpected havens, and one of the most promising lies not in a distant star system, but in our own cosmic backyard. Orbiting Saturn, the small, icy moon Enceladus has transformed from a frozen marble into a world of profound astrobiological potential, thanks to a stunning discovery hidden within old data. For years, scientists have marveled at the dramatic plumes of water ice erupting from tiger stripe fissures near its south pole, captured in breathtaking images by the Cassini spacecraft. These discrete, powerful jets were clear evidence of a subsurface global ocean, but a recent, painstaking reanalysis of Cassini's readings has revealed something even more remarkable. Beyond those iconic jets, the data shows a vast, diffuse cloud of water vapor, a gentle but constant exhalation that envelops the entire South Polar region. This is not just a few geysers, it is a planet-wide sigh, a sign that Enceladus is actively and continuously venting material from its hidden sea across a much broader area than anyone realized. The implications for habitability are immense. This broad plume suggests the ocean's connection to the surface is more extensive and complex, potentially allowing for more consistent chemical exchange between the icy crust and the warm, salty water below. It means the ingredients for life, as we understand it, water, energy from hydrothermal vents on the seafloor, and a rich cocktail of organic molecules already detected in the plumes are not locked away. They are being churned, mixed, and potentially spewed into space where we can sample them. Enceladus is not just a world with an ocean. It is a world that is actively broadcasting its ocean's contents into the void, offering us a free sample. This gentle, global outgassing paints a picture of a far more dynamic and interconnected system than we imagined. A hidden aquatic environment that seems increasingly capable of supporting the delicate chemistry from which life could arise. The gentle outgassing of Enceladus offers a hopeful whisper in our search for life, but the cosmos also delivers more abrupt messages, some arriving as literal impacts. In recent years, our solar system has been visited by travelers from other stars, the first being the strange, elongated object named Oumuamua. Yet we now know that this was not our first interstellar visitor. That distinction belongs to a small, fast-moving object that did not just pass by, it arrived with a collision. Designated CNEOS 2014-0108, this meteor entered Earth's atmosphere on January 8, 2014, exploding in a brilliant fireball over the western Pacific Ocean. For years, it was just another entry in the catalogue of observed meteors, but a meticulous analysis of its trajectory, using precise data from United States government satellites that monitor the sky for such events, revealed something extraordinary. Its speed was the giveaway. This object was moving at over 200,000 kilometers per hour relative to the Sun, a velocity so high it could not have originated within our own solar system. The Sun's gravity could not have accelerated it to that speed from a resting start within our planetary neighborhood. The math was clear and compelling, its path traced back to deep interstellar space. This tiny object, likely less than a meter across, was a confirmed piece of rubble from another star system, and it had reached its final destination right here on Earth. This discovery rewrote the timeline of interstellar visitation, proving that such objects had not only passed through but had made contact years before we even knew to look for them. The implications sparked an ambitious, and some might say daring, scientific quest. A team of researchers calculated the most likely debris field from the meteor's disintegration, a patch of seafloor in the South Pacific over 300 kilometers off the coast of Papua New Guinea. In 2023, they mounted an expedition, using a magnetic sled to scour the ocean bottom nearly 2 kilometers down, hoping to recover microscopic fragments, tiny grains of this interstellar traveler that might have survived the atmospheric entry. The goal is monumental: to hold in a laboratory material forged in the crucible of another star, untouched by our own solar system's history. These specks, if found, would be more than scientific curiosities. They would be time capsules from a distant stellar forge, offering a direct chemical signature of another part of our galaxy. The search itself is a testament to human curiosity, a deep-sea hunt for the smallest pieces of the biggest story, the chance to study the building blocks of other worlds without ever leaving our own planet. These interstellar grains, if ever recovered, would be a direct sample of another star's forge. Yet for the grand architecture of the cosmos, individual stars and their debris are merely the luminous beads strung along a far vaster and darker framework. Astronomers have now glimpsed one of these primordial threads in the process of weaving itself together, a structure so immense it has been named the cosmic vine. This is not a single galaxy, but a colossal filament, a twisting tendril of at least 20 galaxies caught in a delicate gravitational dance. What makes this discovery so arresting is its age. We are observing it as it was when the universe was a mere 2 billion years old. At this distance, its light has been stretched or redshifted to a value of 3.44, carrying a signal from the cosmos in its turbulent youth. The cosmic vine is not a random scattering of islands, it is a highway of matter, a snapshot of the universe's underlying skeleton falling into place. This structure is significant because it is a direct progenitor, a likely seed for one of the massive galaxy clusters we see in the older, modern universe. Within its grasp, galaxies are being funneled together, drawn by the irresistible pull of an invisible scaffolding of dark matter. This is how the universe builds its greatest metropolises, not with sudden collisions, but through these slow, relentless rivers of gas and stars that flow along the filaments of the cosmic web. The vine itself is luminous, but its true power lies in the unseen. It traces the distribution of dark matter, the hidden mass that dictates where normal matter will coalesce. The galaxies within it are being fed a continuous supply of gas from this filament, fueling furious bouts of star formation and likely feeding the supermassive black holes at their cores. To see the cosmic vine is to witness the universe's growth process in action, a living diagram showing how the faint, sponge-like structure of the early cosmos condenses over billions of years into the dense, brilliant clusters that dominate space today. It is a fossil from the age of assembly, a vine upon which the fruits of modern galaxies are slowly ripening. Within the ancient tendrils of the cosmic vine, the first cities of stars were taking shape. Now the James Webb Space Telescope has brought one of these primordial metropolises into stunning focus, a galaxy so distant we see it as it was just 900 million years after the Big Bang. Its official designation is a string of numbers and letters, but astronomers have given it a more evocative name, the Sparkler Galaxy, and the reason is immediately apparent in the image. Surrounding the faint, reddish smudge of the main galaxy are dozens of tiny, distinct points of light, like golden sparks scattered against the velvet black of the early universe. These are not background stars or camera noise, they are individual, brilliant objects bound to the galaxy itself. The profound mystery lies in what exactly these sparkles are. The two leading possibilities each rewrite a different chapter of cosmic history. The first is that they are very early globular clusters, dense balls of hundreds of thousands of ancient stars. In our modern Milky Way, globular clusters are cosmic fossils, relics from the galaxy's violent formation over 12 billion years ago. To see such fully formed, massive clusters already in place when the universe was only 6% of its current age is staggering. It would mean that the process of building these stellar cities was not a slow, gradual affair, but could happen with breathtaking speed and efficiency in the universe's first billion years. The second possibility is equally dramatic. The sparkles could be colossal pockets of intense star formation, regions where suns are being born at a ferocious, almost unsustainable rate. These would not be the relatively orderly stellar nurseries we see in nearby galaxies, but extreme, tempestuous events, forging entire generations of stars in sudden, brilliant bursts. Whether they are ancient clusters or furious nurseries, the Sparkler Galaxy offers an unprecedented laboratory, By studying the light from each individual sparkle, scientists can measure their age, their chemical composition, and their motion. This data provides a direct snapshot of how the very first structures within galaxies assembled. Did galaxies grow from the inside out with a bright core forming first? Or did they build themselves from the merger of many smaller, brilliant clumps like the sparkles we see? The sparkler galaxy, in all its glittering mystery, is not just a beautiful picture, it is a cosmic clock and a blueprint. It holds answers to how the faint glow of the cosmic dawn condensed into the magnificent, structured galaxies we see today, revealing that the universe's infancy was a time of both sparkling beauty and extraordinarily rapid change. That faint, reddish smudge of the sparkler galaxy is a testament to light's long journey across time. But light carries more than just brightness, it holds hidden signatures of the forces that shape it. We saw this with stunning clarity when the same global network of telescopes that produced the first ever image of a black hole unveiled a revolutionary new view. This time, their target was not just the shadow of M87's supermassive black hole, but the intricate dance of magnetism at its very edge. The original image showed a fiery ring of light, a photon sphere where light orbits the gravitational abyss. The new view, however, looked deeper, analyzing that light's polarization. Think of light as a wave rippling through space. Normally, these ripples vibrate in all directions. But when light passes through certain conditions, like the intense environment around a black hole, those vibrations can become aligned or polarized in a specific orientation. By meticulously mapping this polarization, astronomers created a chart of the magnetic field lines threading the swirling chaos of the accretion disk. The result is breathtaking. It reveals a pattern of organized magnetic chaos, like a cosmic fingerprint imprinted on the edge of oblivion. This is not just a beautiful pattern, it is the key to solving one of the most enduring mysteries in astrophysics, the origin of relativistic jets. From the core of M87, a colossal beam of matter and energy erupts, stretching for thousands of light years into intergalactic space. This jet moves at nearly the speed of light, and for decades the engine behind such power was unknown. The polarization map provides the answer. It shows that the magnetic fields near the event horizon are not just present, they are incredibly strong and tightly wound like a coiled spring. As matter spirals inward at tremendous speeds, these magnetic fields are twisted and amplified. They act as a slingshot, channeling some of the infalling material away from the black hole and accelerating it along the poles at a significant fraction of light speed. This process transforms the black hole from a mere consumer into a cosmic powerhouse, a particle accelerator of unimaginable scale. The polarized light shows us the invisible architecture of this engine, the magnetic scaffolding that allows a black hole to project its influence across galactic distances, shaping not just its immediate surroundings, but the entire ecosystem of its host galaxy. The invisible magnetic architecture of a black hole is sculpted by forces of almost unimaginable power, yet similar titanic pressures are at work much closer to home, deep within our own solar system. On the ice giants Neptune and Uranus, scientists now believe it literally rains diamonds. This is not science fiction, but a robust prediction from new laboratory experiments that have recreated the crushing conditions found thousands of kilometers beneath those planets' blue clouds. To understand this, we must journey into an environment where common sense breaks down. The atmospheres of these distant worlds are rich in hydrogen, helium, and simple hydrocarbons like methane. As you descend, pressure and temperature rise to extremes that transform these familiar ingredients. Recent experiments using powerful lasers or diamond anvil cells have shown that under pressures millions of times greater than Earth's atmosphere, and at temperatures of thousands of degrees, the bonds in methane molecules shatter. The hydrogen is squeezed away, and the remaining carbon atoms are compressed into the crystalline structure of diamond. In the depths of these planetary interiors, this process is thought to create a constant, surreal precipitation. Gemstones the size of hailstones or even larger are forged in the upper layers of the slushy mantle and then begin a slow gravitational descent toward the planetary core. This diamond rain is far more than a celestial curiosity. It is a fundamental driver of these planets' very nature. As the dense diamonds sink, they displace warmer material, creating slow, churning convection currents deep within the planetary interior. This movement, this internal weather of falling gems, is now considered a crucial source of the planet's internal heat, and that heat, in turn, is vital for generating their unusual and off-center magnetic fields. Unlike Earth's relatively orderly magnetic field, which emerges from the churning of molten iron in its core, the magnetic fields of Uranus and Neptune are lopsided and chaotic. The diamond rain process helps explain why, by redistributing heat and driving fluid motion in the electrically conductive, slushy layers of water, ammonia, and methane ices. So the next time you see an image of Neptune's serene blue disk, remember the hidden dynamism within. Its beautiful, deep azure Hubble's a hidden furnace where the basic chemistry of life is torn apart and reborn as glittering stones, sinking into the eternal dark and helping to power the very heart of the world. The diamond rains of distant ice giants are forged by immense, crushing pressures, but the galactic core wields a far more violent kind of force, one that can fling entire suns into the eternal dark. This is the story of a star named S5HVS1, a cosmic fugitive caught in the act of escape, racing through the halo of our Milky Way at an almost incomprehensible speed of over 1,700 kilometers per second. It is the fastest star ever detected in our galaxy. To put that velocity into perspective, it is moving so fast it could travel the distance from Earth to the Moon in a mere 2 minutes. This is not a star born in motion. It is a star that has been violently launched, a celestial projectile whose trajectory points directly back to the most dangerous place in the galaxy, the very center. There, shrouded in dust and stars, lurks Sagittarius, a star, the supermassive black hole anchoring our entire Milky Way. The star's path is a perfect forensic clue, a line drawn backward in time that leads straight to this gravitational monster. The likely scenario is a celestial slingshot of breathtaking precision and chaos. Astronomers believe S5HVS1 was once part of a binary system, 2 stars orbiting each other. In a catastrophic game of gravitational billiards, this pair strayed too close to the black hole's event horizon. The immense tidal forces of Sagittarius, a star, tore the binary apart, capturing one star into a tight orbit while violently ejecting the other, like a stone from a sling, at a staggering fraction of the speed of light. This 3-body interaction transformed a stable stellar partnership into a solitary, hypervelocity exile. This runaway star is far more than a record holder. It is a unique probe, a natural experiment sent screaming from the heart of our galaxy. By tracing its exact path and measuring its current velocity, scientists can perform a form of cosmic archaeology. They can rewind the clock, calculating the precise conditions of that ancient encounter near the black hole. This gives us unprecedented data on the gravitational field of Sagittarius, a star itself, the population of stars that dare to orbit it, and the frenetic dynamics of the galactic core. Each hypervelocity star like this one is a messenger, carrying encoded in its speed and direction a story of the most extreme gravity our galaxy has to offer. They are the shrapnel from a cosmic explosion that was not fire and light, but pure, unforgiving gravity. Our galaxy does not merely spin in serene silence, it breathes. From the heart of the Milky Way, astronomers have detected a colossal exhalation, a pair of vast bubbles of superheated gas blowing outward in opposite directions, far above and below the flat plane of our spiral disk. This structure, observed in both X-ray and radio light, is our galaxy's own monumental breath, and its scale is almost impossible to grasp. The bubbles, known as the E-Rosetta bubbles after the telescope that mapped them in full, extend for tens of thousands of light years in each direction. If you could see them in the night sky, they would cover a region larger than the full moon. Within these cavities, gas is searingly hot, radiating in X-rays, while their edges are traced by a shell of cooler, radio-emitting material, like a shimmering boundary in the dark. The origin of this titanic outflow is a story written in energy. The leading theory points to a period of intense activity at the galactic center, a feast that occurred several million years ago. This could have been a burst of frenzied star formation, with thousands of massive stars being born, living brief, violent lives and exploding as supernova in a relatively short cosmic span. The combined energy of those stellar winds and explosions would have been staggering, pumping enough energy into the surrounding gas to blow it outward, carving these colossal cavities. An alternative, or perhaps complementary, explanation involves our own supermassive black hole, Sagittarius A star. While quiet today, it may have experienced an active phase in the relatively recent past, feasting on a large cloud of gas and spewing out enormous jets of energy that inflated the bubbles from within. Regardless of the precise trigger, this galactic breath is not a one-time event. It is a fundamental regulatory process. By venting hot gas out of the galactic disk, the outflow acts as a thermostat for future star formation. Star birth requires cool, dense clouds of gas to collapse under their own gravity. By ejecting this raw material out into the galactic halo, the breath effectively limits how many new stars can form in the central regions. It is a self-regulating cycle where a burst of creation leads to an expulsion that temporarily stifles further creation. This discovery transforms our view of the Milky Way from a static island of stars into a dynamic, breathing entity. We are living inside a galaxy that has a metabolism, with periods of energetic activity that shape its very structure and destiny, reminding us that even our home in the cosmos is subject to cycles of inhaling matter and exhaling energy. This galactic breath is a slow, majestic process, but at the very heart of such structures, destruction can arrive in a single, brilliant flash. In a faint, quiet galaxy far away, a supermassive black hole sat in a state of deep slumber, its monstrous appetite dormant for perhaps millions of years. Its surrounding region was dark and calm, with no swirling disk of hot gas to betray its presence. Then a star wandered too close. The black hole's immense gravity, growing exponentially stronger with proximity, exerted a force so unequal that it overpowered the star's own self-gravity. This is a tidal disruption event, a cosmic cataclysm where a star is literally pulled apart. The side of the star facing the black hole felt a far stronger tug than the side facing away, stretching the star horizontally while compressing it vertically, in a process astrophysicists call spaghettification. The star was not swallowed whole, it was shredded into a long, thin stream of stellar debris. About half of this material was flung away into the void, while the rest cascaded down toward the event horizon, swirling into a sudden, temporary, and intensely bright accretion disk. For a brief period, this dormant monster had a feast laid before it, and the energy released as that material spiraled in and heated up was staggering. The flare of light outshone the entire host galaxy for months, a beacon of violent transformation visible across vast cosmic distances. What makes this particular event so valuable to scientists is its clarity and isolation. Because the black hole was so quiet beforehand, its environment was a clean laboratory. There was no pre-existing chaotic disk of gas to confuse the signal. The brilliant flare acted like a flashbulb in a dark room, illuminating the pristine geometry of the accretion flow as it formed from the stellar debris. Astronomers could watch in real time as the disk assembled itself, measured its temperature changes, and tracked how the black hole's fierce gravity and magnetic fields channeled the material. This provided a rare, pristine template, a textbook case of how matter behaves in the most extreme gravitational field imaginable when starting from a state of perfect calm. These events are more than spectacular fireworks, they are crucial probes. They allow us to study the properties of black holes that would otherwise remain invisible, to measure their masses and spins, and to understand the physics of accretion, the process that powers the brightest objects in the universe from its very first moments. In the terrifying dissolution of a star, we find a unique opportunity to map the darkness that awaits at the center of nearly every galaxy. A star's violent destruction is a testament to the raw power of gravity, but that same force also builds worlds in the quiet nurseries around young suns. The rulebook for this construction, however, is being torn apart by a single, impossible planet. Orbiting a faint, cool star called TOI 5205, a world named TOI 5205b shatters a fundamental expectation of astronomy. It is a gas giant comparable in size to Jupiter, but it circles a star that is only about 4 times the size of that very planet. This is a cosmic mismatch of staggering proportions, a behemoth orbiting a dwarf in a configuration theorists once labeled nearly forbidden. The challenge lies in the very beginning of a solar system's life. Planets form from the vast, swirling disk of gas and dust that surrounds a newborn star. The amount of material in this protoplanetary disk is directly tied to the mass of the star itself. A small, lightweight red dwarf star like TOI 5205 begins with a meager disk, one that seems far too poor in raw building blocks to craft a planet of such immense bulk. According to the leading core accretion model, a gas giant must first form a solid rocky core roughly 10 times the mass of Earth. Only once this core is massive enough can it begin rapidly pulling in and holding onto the vast envelopes of hydrogen and helium gas that make it a giant. Around a tiny star, the disk material is so scarce that building such a colossal core should take longer than the disk itself exists. The gas should dissipate before the job is finished, leaving behind only small, rocky worlds. Yet TOI 5205b is undeniably there, a glaring exception to the rule. Its existence forces astronomers to reconsider the entire playbook. Perhaps planet formation in these sparse disks is far more efficient and rapid than we thought, with material clumping together in new, unexpected ways. Or maybe the alternative model for giant planet formation, known as disk instability, plays a much larger role. This process suggests that under the right cold conditions, a massive disk could spontaneously fragment under its own gravity, directly collapsing into a gas giant planet without needing a large rocky core first. This forbidden world, then, is more than a curiosity. It is a profound clue, a signal that our understanding of planet birth is incomplete. It suggests that the universe has more than one way to build a giant, and that even the smallest, most common stars in the galaxy might be capable of harboring surprising, majestic companions. While gas giants challenge our ideas of planetary birth, the cosmos also broadcasts its own enigmatic signals, some arriving in sharp, brilliant bursts that defy explanation. One such signal, detected in the depths of space, has become a cornerstone of modern astronomy's greatest puzzles. It is a fast radio burst, a fleeting flash of radio waves that crosses billions of light years in a millisecond. But this particular burst, known as FRB 201800916b, is extraordinary for 2 reasons. First, it repeats, sending out multiple bursts from the same location over time, ruling out a one-time cataclysmic event. Second, and perhaps more importantly, it was detected at the lowest frequency ever recorded for an FRB, a deep, rumbling note in the cosmic symphony. Pinpointing its origin was a triumph of precise measurement, tracing its path back to a spiral galaxy similar to our own Milky Way, located about 500 million light-years away. This localization is crucial because it tells us the environment that birthed the signal. It did not come from a dense, chaotic galactic core, but from a quieter, suburban region of its host galaxy, a place where massive young stars are born and die. This context immediately constrains the possible culprits. The leading candidate is a type of neutron star called a magnetar. the collapsed, ultra-dense core of a massive star that possesses a magnetic field trillions of times stronger than Earth. Imagine a star the mass of our Sun crushed into a city-sized sphere, spinning rapidly and wrapped in a magnetic field so intense it could erase a credit card from halfway across the solar system. Theorists suggest that starquakes on the surface of such a monster, or sudden reconfigurations of its magnetic field, could release titanic bursts of energy that we detect as FRBs. The low frequency of this particular signal is a vital clue. Lower frequency radio waves are more susceptible to being scattered or absorbed by material between us and the source. The fact that we can detect them at all suggests the environment around the magnetar, or whatever object is producing the burst, is not shrouded in an extremely dense cloud of debris. It points to a relatively clean neighborhood, which aligns with the idea of a young magnetar born from a recent supernova in a stellar nursery. Each repeating low-frequency burst is like a new line in a complex cipher. By analyzing the subtle differences between bursts from the same source, astronomers can map the turbulent material the signal passed through, both near its origin and in the vast intergalactic medium between galaxies. These mysterious flashes are no longer mere curiosities. They have become precision tools, probing the invisible structure of the cosmos and illuminating the final, furious chapters in the lives of the universe's most magnetic stars. The furious magnetic pulses of a magnetar are a testament to a star's violent end, but a more gentle, continuous erosion can also reshape worlds. Far from the chaotic cores of galaxies, a planet named JWST 69b is slowly dissolving before our eyes, leaving a ghostly trail across the cosmos. This is a hot Jupiter, a gas giant orbiting so close to its star that a full year lasts less than 4 Earth days. Its sun bathes it in a relentless, searing blast of radiation. Using the powerful Keck Observatory, astronomers have now captured a stunning portrait of this planetary transformation. They detected a vast, streaming tail of helium gas billowing from the planet, a plume stretching an astonishing 350,000 miles into space. That is longer than the distance from Earth to the Moon, a comet-like appendage born not from ice, but from the planet's own atmosphere being violently stripped away. This is not a theoretical model, it is a direct observation of planetary evaporation in action. The process is both simple and relentless. The star's intense ultraviolet and X-ray radiation heats the upper layers of the planet's vast hydrogen and helium envelope, giving the atoms enough energy to overcome the world's weakened gravity. The lightest element, helium, detected in its excited state, acts as a visible tracer, painting the path of this atmospheric loss in the light we can capture. Watching this world bleed its gases into space offers a profound glimpse into the life cycle of planets. For JWST 69b, the current rate of loss suggests it is shedding the mass of Earth every billion years, a slow but inexorable change. Over the lifetime of its star, this process could potentially strip away the entire gaseous envelope, leaving behind only a scorched, rocky core, a ghost of a former giant. This observation transforms our understanding of planetary fate. It shows that a planet's environment is not static but dynamic, shaped by an ongoing battle between gravity and stellar fury. For worlds that begin their lives too close to their suns, this gentle, ceaseless wind can be the defining force of their existence, sculpting them from majestic gas giants into barren, rocky remnants over cosmic time. The gentle, stellar wind eroding a distant world is a force of slow transformation, but in the crowded asteroid belt, change arrives through sudden, shattering impacts. This is where NASA's Lucy spacecraft, on its long journey to the ancient Trojan asteroids, made a brief but spectacular stop. Its target was a tiny main belt asteroid named Dinkinesh, a name meaning "you are marvelous" in the Amharic language, a fitting title for what Lucy found. As the probe sped past, its cameras revealed that Dinkinesh was not alone. This small, unassuming rock, barely 700 meters across, had its own even smaller companion, a moonlet orbiting closely around it. The mission team had affectionately nicknamed the asteroid Dinky before the flyby, but the discovery instantly made the name ironic. This was a complex binary world. The images showed the two bodies in exquisite detail, with the primary asteroid revealing a surprising equatorial ridge and the smaller satellite, just about 220 meters wide, nestled in its gravitational embrace. This was far more than a charming celestial snapshot. The discovery of such a tight binary system in the main asteroid belt is a crucial piece of a much larger puzzle, one concerning the violent history of our solar system. Asteroids are the leftover rubble from the planet-building era, and their structures are forensic records of countless collisions over billions of years. A binary pair like Dinkinesh and its moon tells a specific story about mass, energy, and fragmentation. Scientists believe many such pairs are created not from two separate objects gently capturing each other, but from a single parent body being struck and shattered. The impact spins the debris cloud up, and as it reaccumulates, it can naturally form a central mass with a smaller satellite, a process known as rotational fission. By studying the sizes, shapes, and orbits of these binaries, planetary scientists can work backwards. They can estimate the density and internal strength of the original asteroids, calculate the typical energies of the collisions that shape the belt, and understand how mass is distributed among these primitive bodies. Lucy's glimpse of Dinkinesh, therefore, was a masterclass in cosmic forensics. This one quick flyby provided a pristine, close-up model of a phenomenon that is likely common but difficult to study from Earth. It gives context to the countless other faint binary asteroids we infer from telescopic data. Each of these paired worlds is a time capsule holding clues about the chaos of the early solar system, a direct product of the relentless bombardment that once filled the space between Mars and Jupiter. The fact that Lucy discovered this on what was essentially a shakedown cruise for its instruments only heightens the promise of its primary mission: to visit the even more ancient Trojan asteroids that orbit ahead of and behind Jupiter. If a routine test target near home held such a marvelous surprise, what profound dualities and shattered histories await at the frontiers of our planetary system? Deep in the cosmic backcountry, far from any star, a lonely object glows with an alien light. This is a brown dwarf, a cosmic in-between, a failed star too massive to be a planet but too small to ignite the sustained fusion that powers true suns. It is a cold, dark world, adrift in interstellar space. Yet, against all expectation, astronomers have detected the unmistakable signature of an aurora dancing in its atmosphere, a shimmering curtain of light in the perpetual night. This was not seen in visible light, but heard as a rhythmic pulse of radio waves, a beacon of powerful magnetic activity crackling from the void. The discovery is baffling because an aurora on Earth or Jupiter is a product of interaction. Charged particles from the solar wind are captured by a planet's magnetic field and funneled toward the poles, where they collide with the atmosphere to create those shimmering curtains. But this brown dwarf is utterly isolated. There is no stellar wind, no nearby sun to bathe it in a stream of particles. Its brilliant light show should have no fuel. So what is powering this solitary spectacle? The leading theory is as elegant as it is profound. Scientists suspect this brown dwarf is not alone. An unseen companion, perhaps a large planet or even a volcanically active moon, could be orbiting closely. Just as Jupiter's moon Io spews sulfur and other ions into space, feeding the giant planet's intense auroral displays, a similar process could be at work here. The brown dwarf's powerful magnetic field could be capturing charged particles erupting from a nearby world, using this external fuel to paint its skies with light. This turns our understanding of auroral physics inside out. It suggests that these magnificent displays are not solely the domain of planets within stellar systems. They can also illuminate the skies of solitary wanderers, provided they have both a magnetic heart and a cosmic partner willing to share its volcanic breath. The faint radio pulse from that cold, dark dwarf is more than a signal. It is an invitation to imagine a new class of hybrid systems, where a failed star and its active planetary companion together create a beacon of beauty in the endless dark. A supernova is supposed to be a star's final word, a brilliant signature of its total destruction. Yet in a galaxy far away, one star delivered a different message entirely. Known as SN2012Z, this stellar explosion was already peculiar when it was first seen. Classified as a type Ia-X supernova, it was a fainter, slower cousin to the more common type Ia explosions that completely annihilate white dwarf stars. But then, years after its light should have faded into oblivion, the Hubble Space Telescope looked again. To the astonishment of astronomers, the spot in the sky was not dark. It was still glowing and had even grown brighter in ultraviolet light. The star, or something it left behind, was stubbornly refusing to disappear. This behavior shatters the textbook definition of a supernova. In a typical type Ia event, a white dwarf star, the dense Earth-sized core of a dead sun, steals matter from a companion until it crosses a critical threshold. It then undergoes a thermonuclear detonation so complete and violent that no remnant survives. The entire star is vaporized into an expanding cloud of glowing elements. SN2012Z tells a different story, one of a partial explosion, a cosmic failure with profound implications. The leading theory suggests this was a failed detonation. In this scenario, the white dwarf did ignite, but the nuclear flame did not rip through the entire star at once. Instead, it may have burned through the star in a slower, more asymmetric wave, ejecting a large portion of its outer material but failing to completely unbind the core. The result would not be total annihilation, but a severely wounded star. What Hubble is likely seeing now is the hot, bloated remnant of that white dwarf, a stellar survivor that was blasted and stripped by the explosion but held together by its own gravity. This object would be unlike anything we have seen before, a new class of celestial body born from incomplete destruction. It would be intensely hot, rapidly spinning, and possibly regaining brightness as it cools and settles into a new, bizarre equilibrium. This discovery offers a rare glimpse into the physics of stellar explosions at their very edge. It shows that the line between a total blast and a partial one is fine, and that stars can endure cataclysms we thought were unsurvivable. SN2012Z is a cosmic phoenix, not rising from ashes, but refusing to become ash in the first place, challenging our very understanding of how a star's life can end. That stubborn stellar survivor shines as a testament to incomplete destruction, but elsewhere in the cosmos, we find structures that seem to have never truly begun to form. Among the faint whispers of the radio sky, astronomers have pinpointed a ghost, an object officially named J0613+4220. This appears to be a dark galaxy, a cosmic paradox made almost entirely of the raw fuel for stars, yet itself cloaked in profound shadow. Detected by the sensitive 500-meter aperture spherical telescope, its signature is the faint radio emission from cold, neutral hydrogen gas, the fundamental building block of stars. This hydrogen cloud is colossal, spanning a width comparable to our own Milky Way, containing enough material to form billions of suns. And yet, when astronomers point the most powerful optical telescopes at the same coordinates, they see nothing. No pinpricks of starlight, no glowing spiral arms, no central bulge. It is a galaxy-sized reservoir of potential, sitting in the dark, seemingly untouched. Confirming an object like this as a true dark galaxy is an immense challenge. The first question is whether it is truly isolated or if it is just a vast, torn-away ribbon of gas from a past galactic collision. Meticulous analysis of its motion and structure suggests it is a cohesive, rotating entity, held together by its own gravity, which argues for it being a distinct object. The second and deeper puzzle is why it has not lit up. With so much hydrogen, gravity should have pulled pockets of it together long ago, triggering the cascade of collapse that ignites stars. The fact that it remains dark implies something is preventing that collapse. This is where the hidden hand of dark matter becomes the leading suspect. The prevailing theory of galaxy formation states that galaxies are born within halos of this invisible, mysterious substance. The dark matter's gravity acts as a scaffold, pulling in the normal hydrogen gas and providing the deep gravitational well needed to compress it and begin star formation. This candidate dark galaxy presents a fascinating possibility. What if the dark matter halo is present, holding the gas together, but for some reason the star formation process has been stifled? Perhaps the gas is too turbulent or too spread out, or lacks the initial seed of heavier elements that help gas clouds cool and condense. It could be a pristine relic from the early universe, a fossil of a failed attempt at galaxy assembly. The profound importance of such an object lies in its power to test our fundamental theories. If confirmed, it would be a direct probe of the relationship between dark matter and normal matter in the universe's infancy. It offers a unique chance to study the conditions required to turn a cloud of gas into a glittering city of stars. Is dark matter absolutely essential, or can large gas clouds exist independently? How long can a galaxy-sized mass of hydrogen remain dormant before the lights finally switch on? This faint radio smudge challenges the very definition of a galaxy and forces us to ask what, besides stars, makes one. It is a reminder that the cosmos is filled not only with what shines, but with what waits in the shadows, holding the potential for light in a form we are only just learning to see. The potential for light held in a dark galaxy is a profound mystery, yet sometimes the universe's most intricate structures are found in miniature, orbiting the smallest of worlds. The Centaur asteroid Chariklo, a dark, icy body wandering between Saturn and Uranus, holds a secret that defied all expectation. It possesses its own delicate ring system. This was not a theoretical prediction, but a stunning observation made during a celestial coincidence known as a stellar occultation. Astronomers precisely tracked as Chariklo passed in front of a distant star, a fleeting event that would reveal the asteroid's silhouette. They expected the star's light to blink out once as the main body blocked it. Instead, the starlight flickered twice more, briefly dimming both just before and just after the main occultation. That symmetrical double dip in the light curve was the unmistakable signature of two thin, dense rings encircling the tiny world. The confirmation was absolute and revolutionary. These are not the sprawling, diffuse rings of Saturn, but incredibly fine and sharply defined bands of icy and rocky debris, each only a few kilometers wide. They orbit Chariklo at distances of about 400 and 250 kilometers from its center, a miniature cosmic bullseye painted against the dark. The existence of such pristine rings around an object barely 250 kilometers across is a monumental puzzle. Rings are dynamic, chaotic places where particles constantly collide and drift. Around a massive planet like Saturn, the gravity of small shepherd moons can help confine and sculpt the rings, maintaining their sharp edges. But Chariklo is far too small to host such moons, its gravity far too weak to easily control such a system. So what keeps these delicate bands from spreading out, clumping together, or simply falling onto the asteroid's surface? The leading theory is as elegant as it is speculative. The rings may be the recent debris from a cataclysmic collision, perhaps where a smaller object struck Chariklo or where two of its own moons collided and shattered. The resulting debris, confined to a very narrow orbital plane, could temporarily behave as rings. Their surprising sharpness, however, suggests something more is at work. It is possible that tiny, unseen moonlets mere kilometers across are indeed orbiting within the rings or just beside them. their subtle gravitational influence acting as shepherds to keep the particles in line. Alternatively, the rings themselves might generate collective gravitational forces that stabilize their own structure, a delicate self-preservation act. Chariklo's rings force a complete rethink of where ring systems can exist. They prove that you do not need a gas giant's gravity to host such cosmic jewelry, that even small, primitive bodies can be the centers of intricate, dynamic systems. This transforms our understanding of the outer solar system's small bodies from simple, inert rocks into complex worlds with their own miniature architectures, each holding clues to the violent, collisional history that has shaped our cosmic neighborhood for billions of years. Delicate rings around a tiny asteroid show the intricate architecture possible on a small scale, but the most monumental constructions in the universe are forged when entire galaxies collide. In the aftermath of one such cosmic wreck, astronomers have found a pair of supermassive black holes drifting perilously close to one another, a discovery that serves as a living fossil of a galactic merger. These titans reside in the heart of the galaxy NGC 7727, a beautiful, tangled swirl of stars located about 90 million light-years away in the constellation Aquarius. What makes this pair extraordinary is their proximity, not just to each other but to us. They are the closest pair of supermassive black holes to Earth ever discovered. One weighs in at a staggering 154 million times the mass of our Sun, while its companion is a comparatively modest 6.3 million solar masses. For centuries, these monsters went unnoticed because they are not actively feeding. Unlike the brilliant quasars powered by voracious black holes, this pair is dormant, shrouded in darkness. Their detection required a more subtle kind of astronomy. Using the powerful Very Large Telescope in Chile, scientists did not look for blazing disks of gas. Instead, they meticulously mapped the motion of stars swirling in the galaxy's core. By tracking how these stars whipped around at incredible speeds, astronomers could calculate the immense, invisible mass tugging on them. The stellar motions revealed not one, but two distinct gravitational anchors, two separate pits of darkness around which the stars were dancing. This confirmed the presence of the black hole duo. Their current separation is just 1,600 light-years, a mere stone's throw in cosmic terms. This closeness tells us we are witnessing a very late stage in a merger that began long ago. The two galaxies have already smashed together, their stars now woven into the single, chaotic tapestry of NGC 7727. But their central black holes, having sunk to the core through a slow gravitational waltz, are still completing their final approach. Their fate is sealed. In approximately 250 million years, they will finally spiral together and merge, creating a single, even more massive black hole. That collision will be one of the most energetic events in the local universe, not with light but with ripples in spacetime itself. The merger will unleash a torrent of gravitational waves, powerful ripples that will spread out across the cosmos, carrying the signature of this titanic union. Finding this pair is like uncovering a precise clock in the sky, one that is already counting down to a colossal event. It gives us a nearby laboratory to study the final stages of a process that shapes all galaxies. By watching this dormant pair, we learn how often these cosmic dances occur, how black holes find each other in the chaos of a merger, and what the universe looks like in the quiet moments before a storm of gravitational waves is born. This space fossil is not a relic of the distant past, but a preview of a future cataclysm happening in what is, for the cosmos, our own backyard. The quiet, dormant giants of a merging galaxy are a prelude to a distant gravitational storm, but in the universe's youth, the most monstrous black holes grew in secret, shrouded in a thick cosmic smokescreen. The James Webb Space Telescope has now torn that veil aside, revealing the hidden heart of an object known as a hot dog, a dust-obscured galaxy. From the outside, these galaxies appear as dim, red smudges, their brilliant cores completely muffled by vast clouds of dust and gas. They are cosmic furnaces where the building of stars and the feeding of black holes happen at a frantic, hidden pace. Webb's powerful infrared eyes, designed to see the heat glow that pierces through dust, turned its gaze to one such galaxy. What it found was not just a hidden black hole, but a titan in the midst of an explosive growth spurt, a phase of development we had only ever inferred but never directly witnessed. The data revealed the supermassive black hole's accretion disk, not as a faint suggestion, but as a clear, brilliant signal. This was the direct infrared light from the searing hot gas just outside the event horizon, a beacon shining through the dusty shroud. More importantly, Webb's spectrographs detected the chemical fingerprints of powerful winds, vast outflows of gas being driven from the galaxy's core at incredible speeds by the intense radiation pressure from the feeding black hole. This is the moment of revelation. We are seeing the black hole's feedback mechanism in real time from the early universe. As it feasts, it does not just consume, it also regulates. These energetic winds blast outward, heating and pushing the surrounding gas. This accomplishes two contradictory things. In the short term, it can compress gas clouds in the galaxy's outskirts, triggering waves of new star formation. But in the long term, it also blows the galaxy's fuel supply away, eventually starving both future star birth and the black hole's own feast, forcing it into a dormant state. This hidden growth phase explains how the most massive black holes in the modern universe got so big so quickly. They were not just passive consumers, they were active, violent landscapers of their own homes, shaping the very galaxies that housed them through these tremendous outbursts of energy. The hot Digi galaxy, once an obscure red blur, is now a clear window into the messy, explosive adolescence of cosmic giants, showing us that the most important chapters in a black hole's life were written behind closed doors of dust. These 25 glimpses into the unknown reveal a cosmos not of isolated oddities, but of profound, interconnected themes. A powerful common thread is the bending of light itself, where gravity acts as a universal lens. From the solitary black hole warping a single star's light to the perfect alignment that magnified the star Mothra across billions of light years, we see that spacetime's curvature is not just a theory, it is a practical tool. It allows us to weigh invisible wanderers, map magnetic fields on the edge of oblivion, and witness individual stars from the cosmic dawn. This gravitational lensing has become astronomy's ultimate magnifying glass, turning the fabric of the universe into an instrument for seeing the unseen. Equally pervasive is the signature of raw, transformative energy. Across scales, we find systems defined by powerful outflows and immense magnetic fields. The galactic breath of the E-Rosetta bubbles, the diamond rain driving internal heat on ice giants, the violent winds from a hidden black hole in a hot Digi galaxy, even the gentle atmospheric bleed from a doomed hot Jupiter, all speak to a universe in constant motion. Matter is rarely at rest. It is accreted, ejected, sculpted, and recycled in endless cycles that both build and destroy. These discoveries consistently challenge our timelines and rulebooks. The sparkler galaxy's ancient glimmers and the forbidden giant planet orbiting a tiny star force us to reconsider how quickly cosmic structures can assemble. The runaway hypervelocity star and the dormant black hole pair are snapshots of dynamic processes we once thought were too slow or too rare to catch in action. They show a universe that builds, destroys, and rearranges itself with a startling efficiency we are only beginning to measure. And beneath it all, woven through the search from the clouds of Venus to the plumes of Enceladus, is the most human of quests, the search for context. The debate over phosphine is not just about a molecule, it is a rigorous test of our assumptions about chemistry and possibility. The hunt for interstellar meteor fragments is not merely a treasure hunt, it is a drive to hold a piece of another star system. Whether a discovery is firmly confirmed or hotly debated, its true value lies in the boundary it pushes. Each mystery, from the ghostly odd radio circles to the rings around a tiny asteroid, forces an entire field of science to ask better questions, build sharper tools, and imagine more creatively. Together, they sketch a new portrait of reality, one where the unknown is not an empty void, but a vibrant frontier teeming with patterns waiting to be read. This relentless churn of discovery leaves us with a single, undeniable truth. The cosmos is not a serene, static museum. It is a living, breathing arena of ceaseless transformation, a place of unimaginable violence and exquisite beauty intertwined. These 25 phenomena are not isolated curiosities. They are brushstrokes in a grand, evolving portrait of reality. They show us stars torn apart and reborn, galaxies breathing in and out, and entire worlds dissolving in the gentle wind of their sun. Each breakthrough, whether it settles a debate or ignites a new one, does not mark an end. It simply opens a door to a room filled with even more profound questions. This is the true engine of science, the recognition that mystery is not a barrier to understanding, but the very path toward it. Every puzzle solved reveals the outline of a deeper enigma waiting in the shadows. And our tools to explore those shadows are growing more powerful by the day. The next generation of observatories, from colossal ground-based telescopes to even more sensitive space-based instruments, are already turning their gaze to the dark. They will listen for the faintest gravitational waves, map the cosmic web in finer detail, and perhaps even capture the chemical signature of a world that holds life. This journey does not conclude, it simply continues. Our role is to stay curious, to look up, and to follow the light wherever it leads, knowing that the greatest discoveries are always the ones we have not yet dared to imagine.